Now let's talk about the convolution of independent and identically distributed, or IID, random variables. Let's suppose that we want to draw random samples of x with some density fx. Further, let's assume that we further know that x has the same distribution as the sum from I to m of yi's. Here, the yi's, y1, y2, all the way up to ym, are IID random samples from a density fy. In other words, each of them are pairwise independent and they have the same distribution fy. In this case, if we take the sum of the yi's, so in this case, the sum from I equals 1 to m of yi's, and if we further denote that using y star, then this y star, by definition, is known as the m-fold convolution of y. So for this subsection, let's consider the case where the yi's are independent and identically distributed, and y star is the convolution over these IID samples. But you should know that in general, the convolution of random variables, which is the sum of random variables, do not have to be over IID random variables. For example, you can have the convolution of a normal random variable and a logistic random variable. Okay, so back to y star. If we want to say draw samples of x, which follows fx, and we know that y star, which is the sum of the IID yi's, has the same distribution as x, then we can see that we can actually sample the x's by sampling the yi's first and then summing up the yi's. In this case, we can see that the summation from I to m of the yi's, if we call it the function h of vector y, is a special type of transformation we can apply to y. In other words, we can apply the transformation method that we just talked about, which is first draw the yi's and then sum them up to obtain draws from the distribution fx. Sometimes we want to understand what is the distribution of the convolution of IID samples. In classes of mathematical statistics, like 410 or 510, the professors might have introduced a common technique to investigate the distribution of the sum of IID random variables. And this technique is the use of moment generating function, which we call it MGF. Suppose that for a random variable yi, so in this case, the IID yi's, I from 1 to m, they follow some distribution fy, and we use my of t to denote the moment generating function of each of these y's. By definition of moment generating function, we know that my of t is defined to be equal to the expectation of e to the ty. So in this case, for our y star, which is the summation of the yi's, or the convolution of the IID yi's, the moment generating function of y star, my star of t, can be shown to be equal to my of t, so the moment generating function of each individual yi, raised to the mth power. We further know that, like the cumulative distribution functions, which characterize the distribution, the moment generating function also characterizes the distribution. What this means is that if two random variables have the same moment generating function, then it means that they have the same distribution. Therefore, if we can see that my of t raised to the mth power, which is the moment generating function of y star, If this is equal to the MGF of some distribution x that we are familiar with, then we know that y star, which is the summation of the yi's, and this distribution x, who share the same MGFs, are equal in distribution. In that case, drawing from x is the same as drawing the yi's and summing them up. So let's see a few concrete examples. For each of them, let's first identify the distributional equivalence. So sum of some yi's is equivalent to some other distribution. And then let's implement the R code that samples x by summing up the y's. All right, so the first example is going to be the sum of exponential with rate lambdas. So suppose that our IID-yi's each follow the exponential distribution with rate of lambda. Then we know that the moment generating function of each of these yi's, my of t, is equal to lambda divided by lambda minus t, and t can take values less than lambda. This is something that you can memorize, just like you memorize for like the mean and the variance of certain distributions, or you can work out the math and see what exactly the expectation of e to the t y is equal to, and that should be equal to this. Okay, so this is the moment generating function of the exponential distribution with rate lambda. If our y star is equal to the sum of MIID-yi's, then the moment generating function of y star is going to be my of t raised to the nth power, which is equal to lambda divided by lambda minus t raised to the nth power. And it turns out, you can check the Wikipedia page for this, that this is the moment generating function of the gamma random variable with shape m and rate lambda. Thus, we have shown that gamma m lambda and y star are equal in distribution. So if we want to draw samples from the gamma distribution with m and lambda, what we can do is to first obtain IID draws, m of them, from the exponential distribution with rate lambda, and then we can sum them up. So let's try to draw 1,000 samples from the gamma distribution with 5 and 1 as the parameters. Our first step is to draw the yi's. In this case, our yi's will be IID samples from exponential with lambda equals to 1. And we want to have m equals 5 of them to get each gamma random variable. So here's the R code that implements this. It's just 2 lines of code. First, like before, we create a matrix Y, where each entry is a random sample from the exponential distribution with rate equals 1. So lambda equals 1. This matrix has 1,000 rows and 5 columns. So you will know that for each of the 1,000 rows, it's going to be a vector of length 5, where each of them is IID samples from exponential lambda. So now let's sum up each of the rows to get the gamma random variable draws. We again apply the row sums function, and we apply that on our y's. So what this does is that it's going to calculate the sum of each of the rows of y. And we know that each row of y is y1, y2, y3, y4, and y5, which are random draws from exponential 1. So by calculating the row sums, we result in a vector x of length 1000, where each entry is the sum of the 5ID exponential 1 samples in the corresponding row of the Y matrix. In other words, each entry of X will be a gamma 5 1 draw. Let's see if this was successfully implemented. By the way, so before we look at the agreement between the empirical and the theoretical distributions, I have left a optional exercise for you over here. So if you have extra time and want to do some extra exercise, this is what we can do. You can notice here that we drew the exponential 1 samples using the built-in Rx function. So R stands for random and EXP is for the exponential distribution. So this is what we used. Last time when we introduced the inverse CDF method, we actually presented an example for how to draw random samples using the inverse CDF method from the exponential distribution with rate lambda. So your optional exercise is as follows. Instead of using the Rx function to create the Y matrix, try to modify the code and get the Y matrix using the inverse CDF method. As a hint, what you can do is to first create a random U matrix of uniform samples and then apply the inverse transform to this U matrix to get the Ys. All right, so previously we have obtained the X's, and ideally they should be samples from the gamma distribution with shape of 5 and rate of 1. Is that the case? Well, let's try to verify the agreement between the empirical and the theoretical distributions. This time, instead of looking at the density, so the empirical distributions or the theoretical PDF, let's look at the quantiles, the agreement between the theoretical and empirical quantiles using a QQ plot. The QQ plot stands for quantile plot. The x-axis is going to be the theoretical quantiles. In this case, it's going to be the theoretical quantiles of the gamma distribution with shape 5 and rate 1. And this can be obtained using the built-in function Q gamma. The y-axis is going to be the empirical or the observed quantiles of our random draws. Our random draws are the x's, so we're going to find the quantiles of this guy and plot it here. So here's the R code that creates the QQ plot. We first specify the piece, which is a sequence of percentile points or quantile points that we want to inspect. For each of these p's, we want to calculate the corresponding theoretical quantile and the corresponding observed quantile in our X samples. The theoretical quantiles can be obtained by using the Q gamma function applied to each of the p's with the following parameters, so shape of 5 and rate of 1. The observed quantiles again can be obtained using the quantile function, where we again specify the piece, the points that we want to look at. And then we can create a plot where the x-axis is the theoretical quantiles at these points, and the y-axis is the observed quantiles at these points. And here's the output. So forgive me for the super small plot. So there are some default settings of generating Beamer slides with R Markdown. And if I make it too large, then it doesn't show up completely. So the x-axis is the theoretical quantiles and the y-axis is the observed quantiles. We want the two of them to agree, and it seems like they do. So you can see that all of these points, each of them corresponding to each of the p's, they approximately lie on a straight line of x equals y, meaning that the theoretical quantiles of each of these points is approximately equal to that of the observed ones, which is good, meaning that the two distributions seem to agree. Okay, so let's now look at a second example. This time we don't have to look at the MGF, and we just consider the sum of the z squares. So by definition, for IID zi's, which follow the standard normal distribution, the sum from 1 to m of zi squared is going to follow the chi-square distribution with m degrees of freedom. So earlier when we talked about the transformation method, we've seen an earlier example where we try to obtain chi-square degrees of freedom 1 draws by taking the square of the sampled z's. So that is a special case where m is equal to 1. So now let's try drawing 1000 samples from the chi-square distribution with 15 degrees of freedom. And we want to do it using standard normal draws only and transforming the standard normal draws. So here's what we can do. You can see that chi-square 15 should be equal in distribution to the sum of 15 IID standard normal draws squared. So let's first create a Z matrix, which are our standard normal draws. So in this case, Z is going to be a matrix of our norms with, you can see there are 1000 rows and 15 columns. And each of these entries here is going to be a random draw from the standard normal distribution because we didn't specify any mu or sigma, so mean and SD over here. So by default, it will assume mean of 0 and SD of 1. So each of the 1000 rows, again, correspond to the 15 Z draws that we have obtained. And if we square that and take the sum of that row, the resulting x's, which we here obtain by row sums of Z squared, so the Z matrix squared entry-wise, and then we take the row sums. The resulting x should follow the chi-square distribution with 15 degrees of freedom. Let's again try to verify this by looking at the QQ plot. Like before, we first calculate the theoretical quantiles. So this time we use the Q chi-square built-in function with 15 degrees of freedom. And then the observed ones, which we can get from our X samples, that is obtained from row sum of Z squared. And we can create a plot where the x-axis is the theoretical quantiles and the y-axis are the observed quantiles. And this time, because there is enough space for me to do this, let's add a straight line where the slope is equal to 1 and the intercept is equal to 0. So AB line 0, 1. This is essentially the y equals x line. You can see that for the QQ plot, each of these points lie approximately on the straight line, meaning that the empirical and theoretical quantiles agree. Well, we have seen two examples of convolutions of IID samples from in R. Well, aside from these two, so the chi-square distribution, which is the IID sums of Z squares, and the sum of exponentials, which results in a gamma random variable, here are two more equivalencies. First is perhaps a very straightforward one. So the sum of IID Bernoulli trials, so the IID Bernoulli random variables with probability of success P, will be equal in distribution to the binomial distribution with m draws, so m draws, in this case if we sum up m of them, and probability P. And second, the sum of IID geometric draws, geometric random variables, so geometric P's, is going to have the same distribution as the negative binomial. So the MB, standing for negative binomial, with M and P. I included a footnote here in case you forgot what the geometric and negative binomial distribution stand for. The Bernoulli binomial should be quite straightforward. One of them is whether you get a 1 or 0 in one trial, like a coin toss. And the other one is the number of heads or the number of ones you get when you toss the coin n times. Well, for geometric with a parameter P, describes the number of failures until the first success. So the first one, number of zeros until the first one in RID trials with success probability P. And the negative binomial describes the number of failures not until the first success, but until the M success. So how many zeros do I need to get until I get M ones? So you can see that here, if you sum up M of the geometric random variables with parameter P, you get the negative binomial with parameters M and P.